Alright, so you've got an object launched horizontally off a cliff or something driving off of a cliff. So in these problems, it's going to be launched off with some sort of speed. The object's not just getting dropped, it's actually getting launched horizontally with some speed, and then it's going to fall to the ground. So before we solve any problems, let's just talk about what variables we have going on and what happens to them as the object falls to the ground. So the object is usually launched or drives off of the building or the cliff with some sort of initial speed. So it doesn't start from rest, it's moving as it goes off the cliff. So right now we're just talking about an object that's launched horizontally off a cliff, not an object that's launched at an angle. If it's launched at an angle, the problem will tell you that angle. Otherwise, assume it's launched horizontally. Let's talk about the direction of that initial speed. So we're now launching ourselves into the realm of 2D kinematics, two-dimensional kinematics. And that's because our object is now going to be moving in two directions. It's going to be moving horizontally, and it's also falling to the ground vertically. So it's moving both to the right and down, which means we have horizontal motion and vertical motion in the same problem. So when you have 2D stuff, you want to break up X and Y stuff. You want to break up horizontal and vertical stuff. You don't want to mix horizontal and vertical stuff together. You want to look at them separately. Pretend this pen is a car. Pen equals car. This car is driving, and it doesn't see the cliff and it drives off the cliff.
Rather unlucky driver, wouldn't you say?
So let's talk about the initial speed of the car. The speed that the car has at the beginning when it drives off the cliff. So in this problem, we don't care about the car when it's driving off the cliff. We only care once it leaves the cliff and drops off the cliff. The car's driving on the cliff. This is like before the problem starts. So which direction is the car moving while it is on the cliff? Dude. My cat's participating. The cat says the car is moving horizontally, right? While the car is on the cliff, it's only moving horizontally. It's not moving vertically at all, right? Okay, so this isn't part of our problem yet. The problem starts right when the car leaves the cliff. So like right there. The problem starts right when the car leaves the cliff, like the very instant that it leaves the cliff. So my question is, what direction is the car moving at the beginning of the problem? What direction is the car moving right as it leaves the cliff? So we're talking about the direction of the initial speed of the car. While the car was on the cliff, we said that it was moving only horizontally. It had a horizontal speed, but didn't have any vertical speed. So right as it leaves the cliff, the very first instant, it only has horizontal speed. Whatever horizontal speed it had on the cliff when it leaves the table for the very first instant, that's the speed that it still has. So it keeps that horizontal speed the second that it leaves the cliff. So we know it has an initial horizontal speed. Does it have any vertical speed when it leaves the cliff? So does it have any initial vertical speed, or is it just horizontal? Well, if the car was moving only horizontally on the cliff, it had no vertical speed while it was on the cliff, and so the very first moment that it's off of the cliff, it still has no vertical speed. The initial speed of the car, which is right as it leaves the cliff, not when it's still on the cliff, but right as it leaves the cliff, when it's not touching the cliff anymore, its initial speed is only horizontal. It's only got horizontal speed and zero vertical speed. Now, as the car flies off the cliff, that's when gravity can take over and the car is in free fall, and then gravity is going to make the pen gain vertical speed and move downwards and fall to the ground. Right as it leaves the cliff, it only has that horizontal speed. Gravity hasn't had a chance to accelerate it vertically, so it still has zero vertical speed at the beginning. The initial speed is only horizontal. So I keep saying car, but this goes for any object that's launched horizontally, off of a cliff or off of a building. The object could be a green bean, a chair, a bullet getting shot out of a rifle. So at the beginning, this thing has an initial horizontal speed. That is the initial speed that the object is launched with, and it's in the horizontal direction. Now, does it have a vertical speed at the beginning? No, we just said that the initial speed in the vertical direction is equal to 0. Anytime you have something going off a cliff or off a building, as long as it's not launched at an angle, which if it was, the problem would tell you that angle. So I can say that my v naught y, my initial vertical speed, is equal to 0 meters per second. Okay, so a problem is never going to tell you, hey, the initial vertical speed is 0 meters per second. So you have to identify that and write that down. That's super important. You need this fact to solve the problem. So make sure that when you see something launched off a cliff horizontally, that you recognize that the initial speed is only horizontal and that the vertical speed, the initial vertical speed is 0 meters per second. Write this down when you're labeling your knowns. Okay, so what happens to these speeds as the object falls to the ground? Well, as the object is flying through the air, it's in free fall. So the only force acting on it is the force of gravity. The force of gravity acts in the downwards direction. If the force of gravity acts in the vertical direction, the force of gravity causes a vertical acceleration, and that's only going to change the vertical speed of the object. So as the object flies through the air, gravity is pulling the object down to the ground. Gravity is going to speed up the object vertically. It's going to cause the vertical speed of the object to increase, to get bigger and bigger as the object falls closer to the ground. Gravity is speeding it up vertically, and so the vertical speed is going to get bigger and bigger. And right before the object hits the ground, it's going to have the greatest vertical speed. I'm going to call it V final in the y direction. So if the problem asks for the final vertical speed, for instance, the final vertical speed is right before the object hits the ground. Because once it hits the ground, it stops moving. So right before it hits the ground is your final speed. It starts with the vertical speed of 0, but because now the force of gravity can pull it down to the ground, because it's not on a surface anymore, gravity is going to make the object go faster and faster vertically, so its greatest vertical speed is going to be right before it hits the ground. So that's what's going on with our vertical speed. What about the horizontal speed? Is there anything that could change our horizontal speed? Well, no. There are no forces acting in the horizontal direction. There's no force to force the horizontal speed to change. So whatever initial horizontal speed it had, as the object flies through the air, it's going to maintain that same horizontal speed. Nothing's going to change how fast it's moving horizontally. So at any point on the path, the horizontal speed is the same as it was at the beginning. So my final horizontal speed, v final in the x direction, is equal to my starting horizontal speed. So I'm just going to write that fact down over here. V naught x equals v final in the x direction. Horizontal speed does not change. There's nothing pushing or pulling the object in the horizontal direction to change its speed. So however it was moving horizontally, it's going to keep moving with that same speed horizontally the whole time. The only thing that's changing is the vertical speed. If we were in space and this happened, there would be no gravity to pull it downwards, and the object would just keep moving in the horizontal direction forever. But because we're on Earth, gravity is going to pull it down to the ground. The object wants to keep doing what it's doing. It wants to keep going horizontally forever. But gravity's like, no, you can't do that. I'm going to destroy your dreams and make you fall to the ground. Okay, so we've talked about the speeds. What about the acceleration? Remember, we're talking about a 2D kinematics problem, so we want to talk about horizontal stuff and vertical stuff separately. So let's talk about the horizontal acceleration first. Do we have a horizontal acceleration? Well, we just figured out that the horizontal speed doesn't change. it stays the same throughout the entire flight. So, are we accelerating in the horizontal direction? Is there anything to change the motion of the object in the horizontal direction? No, there is nothing changing the motion of the object horizontally. The speed doesn't change, which means that there is no horizontal acceleration. Nothing is changing the horizontal motion of the object, which means that there is zero horizontal acceleration. So what I can write is that my a sub x, my horizontal acceleration, is equal to 0 meters per second squared. Do we have a vertical acceleration? The object has an initial vertical speed of 0, and then it speeds up vertically as it's falling to the ground. So it's getting faster and faster in the vertical direction. So the vertical speed is changing, and it's changing because gravity is accelerating the object to the ground. Remember, if we have a change in speed, that is an acceleration. So we do have a vertical acceleration. And that vertical acceleration is negative 10 meters per second squared. So this goes for any object on Earth. If it's flying through the air, you know the vertical acceleration. It's the acceleration due to gravity. So the key takeaways from all this is that when you have an object in free fall, so nothing's acting on it besides gravity, and you're on Earth, you always know the horizontal acceleration, it's 0, and you always know the vertical acceleration, it's negative 10 meters per second squared. Now, these are true if the only force acting on it is gravity. Like if you have a rocket that has like an engine that's accelerating the rocket, that's not free fall anymore because now you have the rocket engine accelerating the rocket. That's another force giving us a different acceleration. But if you have something, launched out of a cannon or just falling through the air, anything in free fall, your horizontal acceleration is always 0 and your vertical acceleration is negative 10. So when you're doing this type of problem, the object is going to start at a certain height, a starting height. We call that y0, and that's the starting height. How high off the ground does it start? Well, a height is like a distance. And if we're measuring a distance, we need to measure a distance starting from somewhere. So we need a starting point to call 0 so we can measure that distance, so we can measure that starting height. So for all the problems that you do, the best way to go is to call the ground 0. If you call the ground 0, that's your starting point for measuring the height. So the ground is y equals 0, okay? So if the object starts with some starting height of y0 and it falls to the ground, what's its final vertical position? Well, its final vertical position is where it's on the ground, so its y final is actually 0 because we called the ground 0. The object ends up on the ground, so its final vertical position is equal to 0. Again, super convenient to call the ground 0. Do this for your problems. And for x stuff, the object starts at a certain x position, so x0, it's the starting horizontal position. So for horizontal stuff, the object starts with some initial horizontal position x0. And then as the object flies through the air, it ends at some position, let's call it x. So x is the horizontal distance that the object covers when it flies through the air. X is where the object hits the ground. So it starts at x0, ends at position x horizontally. So again, if x is the distance that the object travels horizontally, if we're measuring a distance, we need a starting point to measure that distance from. And that starting point is x0. So if we call the starting horizontal position 0, and we measure distance from here, then x is going to be our horizontal distance that the object covers while it's going through the air, just before it hits the ground. So we've kept x and y stuff separately. Again, don't mix those together. There is one thing that kind of ties x and y stuff together. It's time to talk about the thing that connects x and y stuff together. And that thing is time. Time doesn't have a direction. You don't have an x time, like a horizontal time or a vertical time. Time is just time. Remember, time is a scalar. It doesn't have direction. And the object leaves the cliff or the building, and it takes a certain time to hit the ground. There's only one time. There's no horizontal or vertical time. So you can use the time t for x stuff or for y stuff. It's the exact same time. So we said that all of this is true for any object getting launched horizontally off a cliff. So what does that mean? That means that the mass doesn't matter. It doesn't matter how heavy or how light an object is. Its motion through the air is not affected by its mass, because gravity accelerates all objects at the same rate, 10 meters per second squared. So this could be an elephant or a penny flying through the air, and their mass would not affect their motion. This is what's going on in these types of problems. Now let's solve one using what we just learned.